listen, in particle physics, it's been a slightly lean period, right? You've had people saying it's the death of particle physics. There's nothing that we're going to find, in the years upcoming in particle physics. Is there any reason to have a new, larger LHC, given that we, didn't find all the supersymmetric particles we thought we were going to find at the sort of the energies we were working with? People have been talking down particle physics. It's been a little bit of a lean period. So anything that comes along that suggests new physics is something that gets particle physicists very sort of excited. So they were excited about this last week, and as I say, a lot more excited about the g-2 results, with them being up at 4.2 sigma now. So, so maybe let's have a
So I have a graph or a picture of the ring as it arrived at Fermi Lab. So this was almost 10 years ago, not quite 10 years ago, that the ring arrived at Fermi Lab. It was originally to make the same measurement at Brookhaven National Lab. They used this device, and then they were going to do it at Fermi Lab because Fermi Lab is better than Brookhaven, or as the rest of the world, as far as the rest of the world is concerned, it's because Fermi Lab has a more intense and a higher energy beam. And so like the beam properties that you can get at Fermi Lab are different than what you can get at Brookhaven. And so so they sent this ring that they're using to make the measurement, shipped it to Fermi Lab, and it really reminded me. So it starts in Long Island. You have to go like 1,000 miles maybe to get to Chicago, but because it's a precision instrument, it's not something that you just stick on a truck and drive through the Appalachians. And so the path of the Muon g-2 ring. See if I can have a map. Pull up a map.
So it started off at Brookhaven, didn't it? Which is whereabouts is Brookhaven?
So that's on Long Island.
On Long Island, and then they took it down on a big boat all the way down the east coast of America.
Yeah, all the pictures that they're showing are showing the results that just came out. So had I looked at this a week ago, I would have been able to. The map would have been the first thing that comes up.
And then up the Mississippi River, right, on a big barge. To get it as close to Illinois as they could, which I guess you can get quite close, right? You can go all the way up to. Can you get how?
You can go. So there's a canal that connects the Chicago River to which. So the Chicago River used to feed into the Great Lakes. Now the Chicago River runs to the Mississippi. Fermi Lab. So anyways, the Mississippi River is connected to the Great Lakes, and so they're running on the. I can't remember what the canal is called that connects the two. And this map is still not showing up. So anyways, people will just have to trust me that there was a big map to bring the ring. Oh, here it is. To start from Long Island, down the coast of the United States, up the Mississippi River to this canal that connects it to the Chicago River, and then they took it off and they drove it the last little bit on a truck, and it was a gigantic truck. So the transportation of the Muon ring g-2 Fermi Lab. I'm putting in just a bunch of keywords to see if the right images come up. Okay, here's a good image.
So I can show people watching mine an image of them moving the ring. If I can bring it up in big, I can get a nice big image of it.
So they closed the freeway down. They did it at night. They closed the freeway down. They were driving at like probably half a mile an hour, kind of like taking the space shuttle out to launch. And it had 8,000 tires underneath it to keep it steady. Because anytime it, something gets bent out of shape, that's a lot of money to get it repaired and make sure that it's working properly and everything. And they also, and this is probably the most amazing thing about the transportation of this ring, is that they opened the south gate to Fermi Lab. So Fermi Lab has 3 gates to it, one on the east, one on the west, and one on the south. And a bunch of people who had been at the laboratory for ever since the 1970s, I mean, these are people whose employee numbers are like in the single digits. They were saying, and I was like 12,000, I was employee 12,000 who had gone through there. So one of them was like, I've never, my whole time here, I don't ever remember having the south gate ever be opened. And so it was, locally it was a big deal for the people at the laboratory, like, wow, they're opening the south gate to get this in. So they drove it up and brought it into the laboratory, into a complex that they had been kind of preparing for near the main building on the Fermilab campus. The Wilson Hall is the main building at Fermilab. But it reminded me, the transportation of this ring reminded me of the transportation of the Catron experiment. So the Catron experiment is designed to measure the masses of neutrinos. Let's see, transportation map. And it was fabricated, the main part of the Catron experiment was fabricated in Germany. And the experiment itself was going to be run also in Germany. But because of how precisely the thing needed to be maintained, you didn't want to drive it across the roads, or you wanted to do as little road driving as possible. So it was built just north of Munich in Deggendorf, and it was sent down the Danube River into the Black Sea, around the Mediterranean, up to the Rhine River, through Belgium, to get to Karlsruhe, which Karlsruhe is a German city that's right on the apex of the Alsatian corner of France. And so it went up the Rhine River, was offloaded at Karlsruhe, and driven the last, I don't know, few kilometers to the place. And the size of the Catron experiment was dictated by the space between the buildings in the street that they had to drive on to deliver it to the experiment hall. And so there's a fantastic picture of Catron experiment as they're driving through the last neighborhood, squeezing it in between the buildings. So this is the, so when they transported the g-2 ring from Brookhaven National Lab over to Fermi Lab, it was basically the same thing as the transportation of this Catron experiment. Maybe I should share this with you.
You can share it if you can. If you can share screen, and maybe we can see.
Can I share my screen? I can probably.
So if you go down to the bottom right, there should be a share screen, and you can just share the screen from there.
Is that this? Okay, there's share screen.
We should be able to see.
You can see the whole screen.
Yeah. Oh, wow. So they really had to squeeze it through the neighborhood.
So that's the Catron experiment. And then the Fermi Lab, the delivery of the ring at Fermi Lab was kind of similar, where they had to shut everything down. A whole bunch of people turned out to watch it come in. It came pretty early in the morning, right? They're going to if they're going to shut the freeway down in Chicago, where there's 10 million people, they're going to shut it down at 2 o'clock in the morning.
Yeah.
But the Catron experiment, so here's the path, starts here, and instead of driving the 300 kilometers, they send it down the Danube and all the way around all the peninsulas of Europe, and then took it to Karlsruhe.
Just to go that, 500 miles, if that?
Yeah.
You could have done on the road?
And then this was it, going into the Karlsruhe Institute of Technology, I think is what it, something like that.
Oh, wow.
And there it is. So that limited the size. That limited the size that they could make this. It's a big mass spectrometer. It limited the size that they could make it was that piece. Amazing. Okay, so g-2. Back to this. What is this experiment for, and why do people care about it?
So what we're looking at here is the magnetic moment of the muon. So the muon, for those out there, is essentially the heavier cousin of the electron. In terms of force, it behaves very much like the electron, but it's just, I think, 200 times heavier, significantly heavier. So it's the heavier cousin of the electron. And its magnetic moment should be around 2. This from calculations from the standard model from quantum physics.
Mm-hmm. But because the electron also has a magnetic moment, and it's also around 2.
That's right. And what we know is that actually it's very slightly different from 2. And the reason it's slightly different from 2, its magnetic moment. In terms of magnetic moment, think of it like a a little dipole magnet, right? The muon behaves like a little dipole magnet, and it can spin around in a magnetic field, and it makes its own little magnetic field. Now, what we know from particle physics is that the value is actually slightly different from 2. And the reason it's slightly different from 2 is because the magnetic moment of the muon is changed slightly by all of the virtual particles that are popping into and out of existence around it in what we call the vacuum. We now know the vacuum isn't actually a vacuum, it is an empty space. There's all these particles popping in and out of existence in the standard model and interacting with that muon, which changes its magnetic moment. And depending on how many particles and what types of particles are popping into and out of existence in the vacuum, that changes the value of the magnetic moment of the muon. So if we can measure the magnetic moment of the muon very, very accurately and predict it very accurately with theory, if we see any discrepancy between the two, it must be because there's different types of particles or new physics popping into and out of existence in the vacuum. So it's an indirect way of measuring if there's new stuff and new particles out there in the vacuum.
Right. So now the g-2, so that's the reason it's called g-2, is that you expect it to be 2, so you subtract 2, and whatever's left over is the new physics. Or at least the physics that's higher order in the nature of the interaction. Now, in the electron g-2 experiment, there were some really precise measurements. That's like the most precise measurement that's been made in any science ever, in the history of ever, was the electron g-2, because the calculations were done to 13 decimal places, and the experiment was done to 13 decimal places. And that was actually the Nobel Prize. So the University of Washington, which is where I went to graduate school, they have 2 Nobel Prizes in the physics department now. One of them was, the first one was this g-2 experiment by Hans Deymelt and his group. And so it was after that experiment that we got our new physics building. So they called it the house that Deymelt built, was the electron g-2 measurement. So this is a muon g-2 measurement, which is harder to do. The advantage you have with the electron g-2 measurement is that you can have an electron in a trap and you can keep it there forever, as long as you want. The challenge with a muon g-2 experiment is that when you make a muon, you have 1/1,000,000th of a second to make your measurements
before the
muon decays away. And so the only way to keep the muons around long enough to make this measurement is to get them going at high speeds, because at high speeds, the muon time dilation makes it so that the muon lives longer. You get relativistic effects that make it so that the muon lives longer according to our clocks. Its internal clock is still 1/1,000,000th of a second, but
as I understand it, they even go further than that. So they get the instantaneous pointing of the magnetic moment from the energy and the position spectra of its decay products, so the positrons that hit the wall essentially. So they even have to look at some of the decay products. You're right, because keeping muons around for very long is not particularly easy. So you'll know about this as well. The way they do it is they stick all these muons essentially in a big storage ring and shoot them around, and they have a very high magnetic field, which essentially makes these magnetic moments, think of the muons like little bar magnets, spin around like a top, what we call precession, and we can measure how quickly they rotate around or precess. And therefore we know, if we measure the magnetic field in the experiment very accurately, the only thing that affects that precession speed is either the magnetic moment of the muon or the strength of the magnetic field. And if we know the strength of the magnetic field, we can therefore get an idea of the strength of that magnetic moment of the muon from how quick they're spinning around. And that's what they try to do in the experiment.
So they call this a storage ring, just so that everyone's aware of what it means to store a muon. These muons live for about 60 microseconds. Not about 70 microseconds. It's actually it's 30. The gamma factor was like 34 or something like that. They tuned it to have a particular term cancel out. So a gamma factor of 34 means 34 times 2 microseconds is 70 microseconds. So they circulate around many times because they're traveling at basically the speed of light, 99.97% the speed of light. So they're going around really fast, and they do multiple loops around this ring, but they don't stay in the ring for very long. Okay, so this is looking at when they have these muons that are going around. When the muon does decay, it's going to decay because it sounds like they were using positively charged muons. Is that?
I'm not sure. Do they use anti-muons or do they use muons? I'm not sure.
So I guess it doesn't matter. So the muon is going to be there. It's going to be circulating around because of this magnetic field. When the muon decays into an electron or positron, whatever it is that it decays into, it has the same electric charge. Because that particle has a smaller mass by a factor of 500, it's going to spiral in very quickly. It's going to lose a lot of energy due to synchrotron radiation, and it's basically going to dive into the wall. And so they have all around the interior of the ring is a bunch of detectors, so that when the muon does decay and then that particle slams into the wall, the decay particle slams into the wall, they can detect the location of where the decay took place, and I guess presumably measure some of the spin properties of the.
Yeah, so they can get the instantaneous pointing of the spin of the muon, and then if you look at that instantaneous pointing at a set of points around the ring, just like taking snapshots, photos of it, you can get some idea of how quickly it's processing around, how quickly that spin direction is changing, I guess, in a simplistic way. Mm-hmm. So once you've got that idea of how quickly these muons are spinning around or processing, you can make that measurement of their magnetic moment.
Okay, so there was a picture that they showed in the live stream that was this wiggling decay.
Yeah, you want to share that? And then
let me see if I can pull that up. So they have a bunch of images that show how they measure the magnetic field. Here is the Wiggly Decay, a low resolution version of the. Okay, here's a high resolution. Wow, that's a really high resolution version. This will be great. All right, well, it looked like it was a high resolution version. I guess I clicked on it too soon. It hadn't loaded up all the way. Let's try one more time. 4,000 pixels by 3,000 pixels. So that's the real deal.
Sounds decent.
Maybe we'll just steal this one from the archive. That's better.
Pop it up on the screen and we'll chat through it.
Yeah. Okay. All right, it's not that much better, but here we go. I'll pull it up. And I'm going to switch it to just the window. How do I? Oh, I can slide this. No, I can't. It's not letting me.
It's all right. We can see the wiggly plot. So maybe if you want to explain what the plot is showing.
Hold on, I just ruined it. Right. Oh no, it's still there. Is it still there?
Still there.
Okay.
Yeah, it's still there.
So this plot shows the counts per nanoseconds, counts per 150 nanoseconds. So they're binning it up in 150 nanosecond things. The population of muons is decaying constantly over time. So basically what they do is there's a 150 nanosecond window, and then it gets to the end, and where it ends on the right is where it starts on the left. And that's the next 150 nanoseconds, and then it goes to the next 150 nanoseconds or something like that. So this is, you can see that the decay rate is slowing down. As the population diminishes, you go from one level to the next, to the next, to the next, down until you get basically down into the noise. So you can see the error bars growing on the very bottom thing. You can start to see the error bars in the data that indicate that the population is getting really small, and so you have larger statistical fluctuations. The oscillations up and down are a consequence, I guess, of the spin state of the muon. Is that right?
That's how I read it watching the.
Yeah, let's go with that. So the muon is precessing, and as a consequence, when the decay products come out, you're going to get more or less depending upon how the spin is oriented relative to the magnetic field. And so the oscillations here is the precession rate, and then the decay is the fact that after some number of, after a period of time, the population of muons is going down, and so instead of having one long, really skinny graph, they chopped it up into a bunch of pieces.
So you can imagine, and I think was it Chris Polly? I think he showed this simple model in the seminar. You could fit this graph with essentially a cosine component, which is the wobbling up and down, and an exponential component, which is the decay away of the muons. And that cosine component, which is the wiggling, has your omega inside as its
the precession frequency
as the precession frequency. So looking at this graph and looking at how quickly it wiggles up and down, you can get an idea of how quickly the muons in your experiment are precessing around. And because you know how quickly they're precessing around, and you know the magnetic field that you're applying to them, the only other factor involved is the intrinsic magnetic moment of the muon, which you can now estimate. So this is a really important
this measurement graph. They have to be so precise in the measurement that after they run, is it every couple of days? So they'll run the experiment for a while, and then they'll stop, and then they'll remeasure the magnetic field, and then they do it again, then they remeasure the magnetic field. So they're constantly measuring, like probing the magnetic field, making sure that they understand if the magnetic field, like if the temperature changes a little bit in the room or the humidity changes in the room, how the system breathes, to know that the magnetic field is not changing in a way that they don't understand.
So exactly right. So if you looked at if you watched the seminar yesterday, there was about 15 real world factors on the end of this that they check for the systematics. So the temperature of the ring, as you say, which might change the magnetic field, the electric fields they have to apply on the top and bottom to keep the muons confined vertically, any sort of shaking or mechanical vibrations of the system, all these kind of things that you have to keep in mind so that you know exactly the magnetic field that you applied to your muons. Because if you don't know the magnetic field you're applying to your muons, well, the effect that you're seeing could be either due to a change in a magnetic field or a change in the magnetic moment of the muon, and you don't know which one it is. You need to fix one very, very precisely so that you know that any discrepancy must be in the intrinsic magnetic moment of the muon.
Yeah, and that was something that came out in their discussion of the results, is that the systematic uncertainty, let me see if I can find, they have this figure right here. So the error bars that are shown have two components. One is the extent of the bar itself, and the other one is like the vertical hatchings on it. And I guess the statistical error is the vertical hatch marks. So the statistical uncertainty is given by the error bar that is between the vertical pieces.
I believe so.
So maybe and the systematic uncertainty.
Maybe if you explain briefly what this shows for the people who are watching. Sorry, I didn't mean to go across.
Yeah. Okay. So this is whatever alpha mu is. So this is.
So I believe that's the anomalous magnetic moment. So basically taking away the 2, which is the boring, standard model stuff.
Okay. So you subtract 2 from the magnetic moment that you measure, and this is the difference between the two. So this is g-2 basically. Yeah. And it's a small number, right? It's g-2 minus 1. What? That's 1.165 million.
Yeah. So this is taking away all the other boring stuff that's not.
So these are parts per million. This is like 18 parts per million is the prediction from the standard model. And what they measured is something that is 20 parts per million. So 18 versus 20 parts per million doesn't sound like that much difference, except that their error bars themselves, like their uncertainty in their measurement is, it looks like about a half a part per million. So 500 parts per billion is the size of their error bars. The error bars have two components. One of them is the error bars that come with the fact that they don't have an infinitely large sample, right? They have some sample size, and as they take more and more measurements of their sample, then it's going to decrease, like the statistical error is going to get smaller. So it's very easy. It just takes time to bring the uncertainty in the vertical error bars together. Like to shrink that uncertainty just takes time. If you want to shrink it by a factor of 2, you have to take 4 times as much data. But the systematic uncertainty, so that's the uncertainty in your measurements of the magnetic field, it's your uncertainty in the behavior of the animals crawling around the room, it's your uncertainty in the behavior of the placement of the furniture that's in the room. So all these systematic uncertainties, the temperature variations, how well can you calibrate the probe that you're using to calibrate the magnetic field, those systematic uncertainties, that is the full extent of the error bars. So when you go all the way to the ends of the error bars, that includes the systematic uncertainty. And an important, like, just, I guess, general experimental fact is that once your statistical errors become the same size as your systematic errors, then you're basically done with your experiment. There's no way to make improvements. Any improvement that you make on the statistical side is going to be far outweighed by the uncertainty that you have on the systematic side. And so you basically design an experiment to limit the systematics, and then you run the experiment for the length of time that it takes until the error bars from statistics are similar to the error bars in the systematics, and then you design a new experiment. And so that was what was done here, is that it shrinks, the Fermilab result shrinks somewhat. It's like a 25% shrinking or something like that of the systematic error bars. And then they have their statistical error bars are, basically the same size, but they both agree with each other. The two independent measurements, the measurement that was done at Brookhaven and this new measurement that was done at Fermilab with different energy properties of the muon beam, agreed with the Brookhaven result.
So what we're seeing here, very simply for people, is that the mint green line is what theorists predict the magnetic moment of the muon should be, quote unquote, should be, and then the results on the right in the sort of purpley pink color are what we've actually seen from experiments. So there's a big tension between the two. They don't particularly well agree with one another, and it's becoming more and more unlikely.
How many error bars do you have to go over?
Fluke.
Yeah, it's like
four sigma.
So you have to go. So here's one error bar. You have to go 4 and a little bit times that error bar in order to get into this green area.
So it's becoming less and less likely that this could just be a fluke, and more looking like there's a problem between our theoretical prediction and the experiment. Now, people have come out with a couple of reasons that could be. So some people have suggested that it's the standard model prediction that's wrong. And one reason for that is because it's very hard to make predictions of the magnetic moment of the muon, particularly the strong force interaction terms that go into predicting the magnetic moment of the muon. So I believe there's another prediction that is much closer to the experiment.
That's the one that was shared on Twitter yesterday?
Yes, the BMW collaboration, I believe. So there's some people saying that, look, this could just be a problem with our theoretical prediction of the magnetic moment of the muon. We don't know theory well enough. We're not doing the lattice QCD predictions well enough. That's a boring answer. I hope that's not the reason. I hope it's new physics, but it's a potential explanation. So maybe that one there, Joachim Kopp, if you go up. That one there, Joachim Kopp on Twitter. It's like second row, third across.
Second row, this one.
Yeah, is that the one? Yeah, BMW showing it's
okay,
very
so
close.
let me pull this one up. So this BMW C and this BMW C20 right up at the top.
White paper 20. So there's some theorists who are suggesting that the way that they calculate the magnetic moment of the muon suggests that there's no real tension between the theory and the experimental results that we're seeing. Now, we should know that the mint green that we saw before has a lot of different theoretical predictions in it from different groups with different methods. So this is only one result, the BMW one, that's much closer to experiment, but it still could be that we simply have a problem with how we are theoretically saying what the magnetic moment of the muon should be.
Okay, so let me get that original picture back up. So this is the one that was presented yesterday, 1 day ago. All right, so what you're saying is that the standard model prediction, so typically when you have a model, there's no uncertainty, right? The model predicts a thing, unless you incorporate like quantum effects or something. But in this case, the uncertainty in the standard model prediction is because different groups are using these calculations are not things that you go to the blackboard and run. These are calculations where you build a computer code that does these calculations, and it takes millions of hours of computation time to get through them all. And as a consequence, you have to make certain approximations, or you have to have certain algorithms that are going to produce the different results. And so
so that standard model prediction is an average of loads of different groups
who are simultaneously working on calculating this thing.
Yeah.
And so it's a theoretical uncertainty that's a consequence of the various approximations that different groups are making when they do the calculation.
That's right. However, there is one result in particular, this BMW 20 result, which would be much closer. It would live in that no man's land between the light green and the actual experimental result. So it could be.
Yeah. So the image that they shared had their result was like at this around like 19.5 to 20 parts per million, I guess.
Exactly. So that it could be that this is just a problem with our theoretical predictions. That's obviously the boring answer. And we have to be fair and say that, look, the standard model prediction that's been presented is an average of lots of different groups. So we can't privilege one result over another. We have to stick with that average.
So it's like polling data for elections, right? It's an ensemble of like a bunch of different polls, and some polls are going to have outliers. That would imply that. So I guess where's your money on this?
I mean, science is a conservative, endeavor. You have to sort of say, look, we don't know yet. So, I have to put the money on it being a theory thing, but I really, really hope it's new physics.
Yeah.
And, maybe that's the wrong thing for a physicist to say, because I want the right answer. I'm not going to pollute the waters and say that it is something when it isn't. But I would like it to be new physics. Of course I would, because it's something interesting, something new. We're just going to have to suck it and see, I think.
Yeah, I guess you have the advantage of being an experimentalist, which means that you can sit back and be like, well, we'll just take more data and find out. Where the people who, especially the theorists who do, not the theorists who do QCD, because so they already know what their job is. But the theorists who do like cosmology and astroparticle physics, they're like, here's new physics, here's all the possibilities, and here's how it's going to affect the growth of structure in the universe. To them, this is a playground. All the space between the experimental measurements and the standard model prediction, to them, is not an issue with their code. That's the playground that they have to go around in and come up with new ideas that can explain life, liberty, and the pursuit of happiness.
There's another question that sort of comes up with this, and I wanted to get your sort of thoughts on it as someone who was, more close to this experiment. You've got a Brookhaven result from 20 years ago or whatever it was. You've got a Fermi Lab result from recently, but which is essentially using the same equipment, the same methodology, the same approach. How correlated are those results, and how fair is it to simply take them as independent results? I'm sure this was taken into account in the analysis, but it strikes me that, are they not incredibly correlated?
So I guess it can depend, right? You're always going to store a muon in a ring. So like there's geometry issues to be perhaps concerned about. I suspect it's not like the spin of the protons coupling, or the spin of the muons coupling to the spin of the Earth, if you had some kind of weird spin-spin interaction. I guess that's a possibility, but it probably would have turned up somewhere else.
Is it fair to say that the Fermi Lab result is a new result, or is it just an emulation?
Or like, is it a superposition of a correlated result and a new result?
Correct. Yeah.
So it's because the same thing arose with the DAMA dark matter experiment, where they made DAMA. They had some special kind of crystal that you can only grow in the orchards of northern Italy and the vineyards of northern Italy, and so they saw a signal. It's like some sodium iodide detector technology that no one else had built. So the DAMA results came out like late 90s, and then they rebuilt it, the Libra experiment, using the same detector, and they saw the same signal. But no one else who is presumably just as sensitive, except they're using germanium or something like that, that they didn't see it. And so there is that's another example of an experiment where they built it, and then they built it again with using the same detector, not necessarily the same design or surrounding the detector, but the same detector technology. And so, yeah, I think it's a fair point to make that they are using a lot of the same equipment. I think some of the differences, some of the things that I think would point to this as a completely independent result, if I were to argue for the defense in this case, would be that the beam's at a different energy, and there you go, the beam's at a different energy. They probably had different calibration things in terms of like what systematic effects might there be and how can we improve upon the calibration that they had before. So my understanding of like deciphering all of the stuff that went into the discussion when they announced the results was that the Brookhaven experiment, they had to measure also the electric field, like the local electric field. And as a consequence, they were limited to some extent in their uncertainty, their systematic uncertainty, by their ability to measure that electric field, because they couldn't get the beam energy high enough to cancel that out. And where at the Fermilab results, they chose a specific beam energy specifically so that it would eliminate, because it's basically the term has an electric field and then a beam energy term, electric field term and a beam energy term. And
it was a term over like gamma squared or something.
Right.
If you make gamma big enough.
And so they made gamma bigger so that the term drops out and it basically drives it to zero. And so that's something that eliminates one of the systematic effects that had been present in the Brookhaven result that's gone in the Fermilab result. And so I guess in all experiments, it's a matter of playing whack-a-mole with, as the sensitivity improves, as you eliminate certain systematic effects and your error bars shrink down, you uncover new systematic effects. Like there's some other thing that now you have to worry about the fact that, well, here's an example. In gravitational torsion pendulum experiments, there was the group at the University of Washington made an experiment where they designed like a bunch of pizza slices. So they had a puck that was a bunch of pizza slices made out of magnetic material, and they arranged the magnets so that the magnetic field would cancel itself. However, the way that the magnetic field was generated by the different material was, in some of it was generated by the orbital motion of the electrons, and in some it was generated by the spin of the electrons. And so you have spin component of a magnetic field and an orbital component of the magnetic field, and then you have them cancel each other. So the magnetic field cancels, but now you have a net spin. So you have a pendulum that has a net spin from the spin of the electrons. And what ended up happening was they started making measurements, and the spin of the pendulum, the spin of the electrons in the pendulum, coupled to the spin of the Earth. And so they're like, we get this really anomalous signal that points due south. And it was this spin-spin coupling of the pendulum to the rotation of the Earth, like the quantum spin of the electrons coupling to the rotation of the Earth.
Sounds crazy.
Yeah, I mean, so it's cool though, isn't it?
So it is a fair question of how decoupled these results are, and you make a good case that they are relatively decoupled. But in the end, it comes back to the same thing that's going to happen with the LHCb result. If it gets up towards 4, 5 sigma, you're going to have independent verification from an experiment that has completely different technology inside, completely different methodologies for calculating this thing. So one thing people don't realize at the LHC is that we have ATLAS and CMS. And when we discovered the Higgs, they both discovered the Higgs. So we had ATLAS and CMS with completely different technologies inside them, different methodologies for looking for the Higgs, which independently verified that they'd found this thing. So you could have a lot more confidence that whatever systematics there were between the two were different, and you were still getting this result.
And the same thing happens with the results at Fermilab. They had the CDF and the D0 detectors.
Yeah, exactly.
That were designed to look for different processes, and as a consequence, when they did the analysis, it's like, well, we were looking at, the interaction with the Hubble particle, and this other one was looking at some other kind of interaction that would both give you a signal, but through different processes, and then they could analyze them together. Now, so one of the questions came up is, all right, so they've made this detection. So what? So the g-2 disagrees with the theory, or at least disagrees with the ensemble of theories, if not with every individual. So this, one of the things that this does, I guess, is forces the theorists to get their act together in terms of, we need to come to better agreement between our, so we have 10 groups that are working on it, and we all disagree with each other to some extent. It hasn't been a big deal because there hasn't been any guidance from experiment.
Yeah.
And now they have guidance from experiment. There are 2 data points that are that you have to contend with, and so that's going to drive the theorists to come to a better agreement with each other. So that's one consequence of this. That's a consequence that's perhaps only important to a few hundred scientists. So, but what about the physics? If this is a real anomaly that deviates from the standard model, then what?
Well, so it suggests that there's some other physics going on, potentially some other particle or some other force. As you say, not only does it force the theorists to get their act together, but it potentially gives some signposts for where new physics could be hiding. Now, I'm not very much up on my g-2 best theories that could have accounted for this experiment, but I'm sure there's a lot of theorists sat there going, well, my theory, would fully account for this. So there will be various theoretical frameworks that explain this particular anomaly and will, as I say, give signposts to where new physics might be hiding. I've heard people talking about potentially a second Higgs. We've talked about the fact that this could be an issue with the theoretical calculations. At the moment, it's unclear, but there's a lot of theoretical frameworks that could potentially explain it, and those are going to be the ones that obviously get a little bit of more work put towards them and have people sharpen up and clean up that work to try and explain this.
So I guess, for example, you'd have...
It's always that to and fro, right, between theory and experiment.
So like the anomalous magnetic moment is some diagram that looks like this. And so what you would be looking for is, so here's the muon, the magnetic moment, right? Here's the coupling to the magnetic field at the top. And then the issue is, if you include all of the known interactions in the standard model, that's all the stuff that goes into this junk down here.
This bubble g-2.
Yeah, this bubble g-2. And so what it implies is that there's interactions that aren't known about in the standard model. So there's some other particle. It could be a leptoquark. So that maybe there's...
So your g-2 box, that yellow bubble, is more populated with random stuff than you thought should be possible given the standard model.
Which would include a new type of particle that couples to the electromagnetic field, apparently. If it has to couple to the electromagnetic field, maybe it's coupled to something else. But there's some new particle that goes in this diagram down here at the bottom. Maybe it's, so if it's a new force, then that would imply that there's some other coupling to the muon that goes to this particle. A new force would be pretty gnarly, because there's only 4 forces known to nature, and only 3 of them that are known to be quantum in origin.
Yeah, one of them we don't talk about. He's the naughty child. Gravity we don't talk about.
But so having a new force, that would be pretty cool. Or having a new particle would also be cool, like a particle that has a particularly weak coupling to the electromagnetic field, but it nevertheless contributes to this, and that might give us some indication. Maybe there's a dark matter particle that has a very weak coupling that you can get to in this diagram that then would contribute to the magnetic moment of the muon.
It's a really good question, right? It sounds like a who cares, what why is it important question. This is an indirect measurement, right? It's not telling us exactly why it's different or what's causing it. It's just saying it is. So it's very difficult to explain, and it'll take a lot more work to unravel than, when we found the Higgs, we were like, we already had that tailor-made ready. We know pretty much what this is.
Yeah, no surprises
there. With
this,
it's a signpost saying, please go look more in this area, rather than a definite, it's A.
So when a scientist, like when a particle physicist says new physics, they're talking about like new discovery. And in the case of particle physics, a new discovery is huge. It's more than, I think it's fair to say that the discovery of a new particle, like a new fundamental particle in particle physics, is more than just discovering a new chemical element, right? There are there's 100 and something chemical elements and something like 1,000 different isotopes. This would be like discovering, it'd be like coming home and be like, oh, we found a new family member in our house. You know, like
things fall upwards now.
Yeah, this is it's a completely like a new particle. When you only have 10 particles to work with or 16 particles to work with, it's a much larger contribution or change to things, especially in a situation where we're living today, where 95% of the energy density of the universe, we don't know what it is. And so 95% of the stuff that's out there could be in this anomaly in the G-2.
So it's very, very intriguing. And new physics, people throw around that word, you know, new physics beyond standard model physics. We need it because there's things that the standard model can't explain. You touched on a couple there, you know, dark matter, dark energy, the nature of gravity. We know the standard model isn't the be all and end all in particle physics. So any signal that we can find that shows us where to go after that model, as successful and brilliant and precise as it's been for so long, you know, is a very, very useful signal. Mm-hmm. And as I said, it will give us some signposts as to where to go next. That doesn't undermine how important and, you know, formative and brilliant the standard model has been. It's just that we know it can't be the final word.
Yeah. So a question came up, and I guess this is probably the op-ed time, would be, what is more important in the long run? I get, so what's more important, the discovery or the characterization? So you discover new physics and then without the understanding, or the understanding that comes from later experiments?
I guess it would have to be the understanding, wouldn't it? Just finding something doesn't, you know, have we learned anything new? We just know something is there. Unfortunately, without having that sort of slap in the chops, as you said, to look, this is where you need to look, this is where you need to focus your energies, this is what you need to explain. You know, how do you even do that? It's like telling someone to invent something without telling them what to invent. Mm-hmm. You need some sort of spur of where to look, some clues as to what your theory should be able to predict. You know, so they both go hand in hand. As I say, there's always that interplay between theory and experiment. You know, so both are important, but I think in the end you want to get to that point, because physics is about explaining why the universe works, of being able to explain, you know, why an experiment has given the value that it has. So the end point is the categorization, I guess.
Yeah, and the same thing kind of has come up in exoplanet science, where so 1995 is kind of the breakout year for exoplanet science. There were certainly hints of exoplanets in previous years, but 1995 is the canonical start of the field, like the first discoveries in the field. And for about a decade, probably 15 years, it was all about discoveries. If you discovered a new planet, you were famous. That was what it came down to. Is like the discovery of every new planet was, that was how you made your name.
Because it was novel and something new and something people didn't know was out there, right? So there's always that.
And that's no longer true. It's no longer true that just making a planet discovery is viewed as important as it was back then. And so now it's more like, now that we have these planets, you do the analysis of the population to understand how does that affect our understanding of planet formation. And so, but the Nobel Prize is not given really for the understanding of the that comes from it. It comes from, I guess, opening the door or blazing the trail. So
I mean, taking the example of exoplanets. I mean, I don't think you can underplay, you know, how exciting, particularly in that sort of field in astronomy. Where people can. We've both got a friend, Dave Kipping, who does these videos that are very, sort of aspirational and cool music in the background, and it's all the meaning of life and all these sort of deep things. I don't think you can undersell how much just finding those things in that field made people think, I want to be involved, I want to know more. Mm-hmm. We need to get out there and understand more about where these things are coming from. Potentially they link back to where we came from in terms of life developing. So there's no doubt that they can spur on that understanding. So they're incredibly important. There's no doubt about that. I mean, we see the buzz about this, on Twitter, and it's all over the media, this G-2 results from yesterday. But the end point has to be the categorization. And I guess what you're sort of alluding to is that now in astrophysics, people are saying, hang on, why are those planets that we found like this? How did they develop? How many of this type are there and how many of that type are there? And this type of thing has become more important, that categorization, more than, oh, we found another one to put into the box.
Yeah, there's definitely something to go along with the thing that inspires public interest isn't always the thing that inspires or motivates the scientists. I can assure you that there's at least one person in exoplanets who really doesn't care about alien life. And
it's not Avi, is it?
No, it's me.
Oh, right. I've seen Avi getting some stick over the last few months. I haven't followed it too deeply, but
so
Avi Loeb or Loeb. Or...
I mean, maybe I shouldn't say this out loud, but I'm just not interested in the search for alien life. There might be some technical questions that I think would be interesting to see, and I certainly I understand how people can be interested by it. I'm not I understand that people dig that kind of thing. It's just I can understand how people like certain types of food, even if I don't really care for that.
But it's not your cup of tea, as we'd say over here.
Right. That's not the thing that motivates me to study exoplanets. So, to each their own, which is good. You don't want to have everybody studying exactly the same thing, or else you only learn those things. You want to have the variety that's out there. But there are, those are the things like discovering planets, and maybe there's life on the planets. These are important questions for other people. And I'm willing to even, I even devote some of my work on, I've done papers on, or a paper on panspermia. I've done papers on habitability, because I recognize that they're important scientifically, even if it's not personally, it's an aspect of my research that isn't the thing that gets me up in the morning, but you still do a good job. Vacuuming the floor, you do a good job vacuuming the floor, even if it's not the thing that you enjoy doing the most. So, and discovering life is probably more interesting than vacuuming the floor, to be fair. But so just because though a particular scientific question isn't necessarily the thing that you care the most about, you can still do a good job, and people can, you can still recognize the importance that it has for others.
As my mum says, it takes all sorts, Jason. It takes all sorts.
Yeah.
So if everyone was like you, Sam, the world would be a very boring place. And I agree with that. So.
Hey, I really appreciate your time. Is there anything else that you want to say? Do you want to do a shout out for my stream of who you are and where they can find you?
Yeah. So my name's Sam Gregson. I worked on the LHCb experiment over at CERN. I now have my channel on YouTube, which is Bad Boy of Science. So pop over there. You can find me on Instagram, Twitter, all sorts. But yeah, pop over to YouTube, Bad Boy of Science. You're always welcome, especially if you disagree with me. And, we have Jason over a decent amount. And we're always looking to discuss the next scientific thing that's coming down the track.